Welcome to the lecture of Renewable Energy System. In today's lecture, we will talk about the classification of hydropower plants. Hydropower can be generated wherever a flow of water descends from a higher level to a lower level. The difference between the two water surface elevations is referred to as head. Head can exist in nature, for instance, when a stream runs down a steep hillside or when a sharp change in elevation creates a waterfall in a river. However, head can also be created artificially by constructing a weir or dam. The dam creates a barrier to water flow, raising the upstream water level to the desired elevation. As a result of elevation, different gravitational potential energy is stored in the water. This energy can be used by installing turbines and generators. Water flow moves the turbine blades, thereby converting water potential energy into kinetic energy. The turbine rotational forces the generator rotator to spin around the stator, thereby converting kinetic energy first to mechanical energy and then to electrical energy. We can classify installation in different ways by the head of the water or by the capacity of the hydropower plant or rated output power. The hydropower can also be classified by the type of the turbine and by the location and type of the dam or reservoir, etc. These categories are not independent of one another. The available head is an important determinant of the other factors, and the head and output largely determines the type of the plant and installation. Flow rate and head are influenced by reservoir inflow, storage characteristic, plants and equipment design features, and flow restrictions imposed by irrigation, minimum downstream release, or flood control requirement. Historical daily seasonal maximum flood and minimum drought flow condition are carefully studied in the planning stage of a new development. Plant capacity, energy, and physical features such as the dam and spillways structures are optimized through complex economic study that consider the hydrological data, planned reservoir operation, perform characteristics of plant equipment, construction cost, the value of capacity and energy, and financial discount rates. Another important planning consideration is the selection of the number and size of generating units installed to achieve the desired plant capacity and energy, taking into the account installed unit cost, unit availability, and the efficiencies at various unit power output. The generating units may have its shaft oriented in a vertical, horizontal, or inclined direction depending on the physical condition of the site and the type of the turbine is applied. Hydropower plants are commonly classified based on installed capacity in megawatt. Opinions varies on the threshold that separates individual classes. Hydropower plants are also classified based on the dam heads as stated before. The classification mentioned here is approximate but widely accepted. However, criteria may vary among countries. Micro hydropower plant has installed capacity less than 0.1 megawatt. The installed capacity of small hydropower plant is between 0.1 megawatt and 10 megawatt in some countries. It can go up to 30 to 35 megawatt. The medium hydropower plant capacity is between 10 megawatt and 100 megawatt, and large power plants have capacity more than 100 megawatts. Micro hydropower projects can supply electricity for an isolated industry or small remote communities. Usually, micro plants are standalone, that is, they are not connected to the grid and they are always run of river type. Small water storage tanks are sometimes constructed so that hydro generation is guaranteed for minimum period per day, even during low water flow conditions. Micro hydropower schemes are commonly encountered in rural areas of developing countries where they provide an economical energy source without fuel dependency. Small hydropower plants are dimensioned considerably smaller than medium and large hydropower plants because small hydropower plants usually use low discharge. Most small hydropower plants are run-of river type that are connected to the power grid. Medium hydropower schemes are either of the run-of river or storage type, and they almost always feed into a grid. Their layout may include a dam to create a head pond, although projects under 100 megawatt would generally not be considered by developers to be large. Some European Union guidance related to the clean development mechanism required additional assessment for projects over 20 megawatt. Large hydropower schemes are always connected to a large grid. Large hydropower plants can be run-of-river or storage type. Each layout is site-specific and each plant's electrical and mechanical equipment is designed for local needs and conditions. Depending on the head being used for electricity production, hydropower plant schemes are divided into three categories. That is, high head in which head height is more than 100 meter. The medium head dam has head height between 30 meters to 100 meter and low head height is 30 meter. However, like classification based on power output, definitions can vary by country and organization. The International Commission on Large Dam defines a large dam as one greater than 15 meters in height. Also, classifying hydropower plants according to head may be inconsistent with classification based on power capacity. Power capacity is proportional to the product of available flow and head. Hence, even high head installation might be characterized as micro or small hydropower plants. A small head hydropower plant is shown in the above figure. This dam is located in German city named Tübingen. The low dam or barrage of the installation services to maintain a head of water and also the houses of the plant. The head is less than 30 meters. This type of installation is mainly used for run-of-river power station. The disadvantage is that they have only little storage capacity and are dependent on the prevailing flow rate. This can present problem of reliability if the flow varies greatly with the time of the year or with the weather. The large volume flow through a low head plant means that the plant and the associated civil engineering works are large too. Typically, mountainous terrain provides conditions necessary for implementing high head or medium head hydropower plant schemes, often storage type. Lowland areas with wide river valleys provide location feasible for installing low head scheme. This type of installation is typically used for very large hydroelectrical installation with a dam at a narrow point in a river valley. The large reservoir behind the dam provides sufficient storage to meet demand in all but exceptionally dry conditions, which ensure a reliable supply. It will also have flooded an extensive area. The USA has some of the largest dams of this type, including the Grand Collet, which is 170-meter high and create a reservoir that stores 9 billion cubic meters of water. Systems of this type don't have to be on a giant scale, and quite small reservoir can provide power for hydroelectrical plants. In the high head power plant, the entire reservoir lies well above the outflow level, as shown in this diagram. You can see the reservoirs are very low and they have a lot of height as compared to the outlet of the turbine. With the high head, the low the flow needed for a given power is much smaller than for a low head plant, so the turbine, generators and housing are more compact. The penstock carrying the water may even passes through a mountain to reach the turbine, but the long penstock added to the cost, and the structure must be able to withstand the extremely high pressure below the great depth of water as much as 1000 kilopascal for 100-meter head. We may also have some efficiency losses in the penstock. Hydropower plant schemes can be classified according to the type of operation as follows. Number 1, the run of the river scheme. Number 2, storage scheme. And number 3, pump storage scheme. Run of the river schemes generate electricity by immediate use of the inflow. As a result, run of river hydropower plants are subject to weather and seasonal variation, resulting in variable power generation. Most run of river schemes have no storage capacity or limited storage, which limits peak power operation to a few hours. Storage schemes are characterized by water impoundment upstream of a dam structure to create a reservoir in which water is predominantly stored during high flow period and consumed for energy production during low flow period. Using stored water for the inflow to generate energy creates some security against natural fluctuation in water availability caused by weather and seasonal variation. Reservoir size determines the level of flow regulation as well. Pump storage plants are hydropower plants that can store water by pumping it from a lower reservoir or a river to a higher reservoir. Water is pumped during off-peak hour by reversing turbine operation to make more water available to generate electricity during peak demand period. Off-peak hours are in which power demand is lower and the supply price is also lower. Pump storage process creates efficiency of up to 80% in which pumping use 20% or more energy than the energy that is generated when an equal amount of water is released to generate electricity through the hydropower plant. In terms of electricity production, storage schemes can provide peak energy at a planned and required time, while run-of-river hydro plants can be used for generation only when water is available. A reservoir of stored water determines the potential for peak power supply on daily, weekly, and monthly periods. Reservoir volume is directly related to the required period of peak power generation. Multipurpose schemes provide water for other use for human life and development. The hydropower plant can also be classified by the purpose. About one-third of existing hydropower plant projects serve other functions in addition to energy generation. The additional function of hydropower plant schemes may include the following. Number one, the flood protection. The water storage reduces the impact of the floods. For drought mitigation, hydropower plant supplements irrigation and community water supplies during dry period. Hydrowater reservoir is utilized for agriculture. Another purpose could be the reservoirs also provides water supply to community. Last but not least, raising the water level in a reservoir improves condition for navigation, fishing, tourism and sport. In today's lecture, we have discussed about the classification of hydropower plants according to its head, capacity and operation. Today's lectures end here. Thank you for listening.